So, hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to discuss the sufficient condition for convergence of the Gauss-Jordan method. So, let us discuss that one. So, in the previous lecture we have discussed the definition of diagonal dominant matrix. So, now today I am going to discuss that how the diagonal dominance matrix is used to show the method Gauss-Jordan, Gauss-Jacobi basically. Gauss-Jacobi method. So, it is not the Gauss-Jordan, Gauss-Jacobi we are talking about. So, suppose I have a matrix A and that matrix is a n cross n, and we have a system of equation Ax is equal to, so this is n cross 1 and this is n cross 1. So, this is my system, and this system is a very big system. It is not a 3 by 3 matrix, or it may be a million by million matrix. So, in this case I want to solve this system to find out the solution. So, in the real applications we always go with this type of matrices, that is the dimension of the matrix we can have a very large dimension. So, we apply the iterative process. So, in the Gauss-Jacobi method, suppose we have this one. So, I can write this matrix as A11 x1 plus A12 x2 A1 xn, that is suppose equal to B1. Similarly, we can write A21 x1 A22 x2 A2n xn is equal to B2, and I can write here an1 x1 an2 x2 and ann xn is equal to bn. So, this is my corresponding system of equation. Now, what I am going to do is that in this equation, so from here I am just keeping these things on the left hand side and taking the other terms on the right hand side. So, what I am going to do is that I am going to have here x11 is equal to, I can write as a b1 minus taking all the terms on the right hand side. So, this one I can write as summation all a I j x j. Now, I can write from here that I is moving from 1 to, so in this case I can have this j. So, basically I will take j from 1 to n, and I can write that the j is not equal to I. Okay. And this is true for all I. It means suppose I am taking here, so it is 1 2 1 3. So, I can write here so just I will write j, or maybe I can write from here 1 j. So, this one I can write, and then divide by A11. Okay. So, my matrix A11 is not equal to 0, and also, so this is my matrix, and also I am writing that suppose matrix A is diagonal dominant. So, this definition we already know that what is the diagonal dominant. So, suppose we are considering also that A is diagonal dominant matrix, and then we are going to write the Gauss-Jacobi method for solving this system iteratively. So, I can write like this one. Similarly, from the next equation I can write my x 2 2. So, that can be written as B2 minus summation. So, it is 2 2 2. So, I can write from here, and I can write j is not equal to 1, whatever the 1 is there I can not take. Okay, so maybe I can write here, just for the indexing I can write from 2. Now, from here I am taking x22. So, I am writing here again j is from 1 to n a 2j xj divided by a 22, and I can write that j is not going to be 2. So, all this I can write in the form of this equation. So, it will be Bn summation j from 1 to n a nj xj and then divided by a nn, j is not equal to n. So, whatever the I am taking, this will corresponding to this system. So, now from here this becomes that how we can write our system. Now, based on this system I can make this system in the iterative form. So, from here you can write this as, so each equation can be written now. So, I can write this equation as, so now we can write the iterative scheme how. So, I am finding x, that is maybe I should write here not x11, it is x 1 2 n. So, this one. So, I can write my x k as b k minus summation j from 1 to n a I j x j, j is not equal to I divided by a I and this is true for all I is equal to 1 2 up to n. So, this one I am writing, or maybe I can write this as, because I am writing I. So, I should write here I only, not k. So, I will write I. So, my x I is equal to b I minus this part where j is not equal to I. So, this is the corresponding system. This system I have written with the single equation. Now, based on this equation, now I want to make it the iterative process. So, in the iterative process what I am going to do is that, suppose I am finding at k plus 1 step and this value is given to me at the k step. So, this is corresponding iterative schemes we get. So, this is my iterative scheme. Now, so this is my iterative scheme. Now, let I introduce the error terms, error E I am taking. So, this is, suppose I am calculating at the k plus 1 step, that is equal to I am finding the value of x I at k plus 1 step minus this is the exact value. So, this is the error we are taking. So, basically this is exact solution. So, this is the solution basically exact, because in the iterative scheme we are going to improve our solution starting with the initial solution, and this is the exact solution. Whatever the solution is there, if we are able to solve the system exactly, then this is suppose the exact solution, and this is the solution at the k plus 1 step, and I am taking the error ei at that time. Now, so this equation I can give the name as equation number 2. Also, I can write my xi is equal to bi minus summation j from 1 to n, and j is not equal to I, a ij xj divided by a I, where I is 1, 2 up to n. So, this equation I write 3. Now, 2 minus 3, I subtract this equation, second equation minus the third equation. So, what I will get is, I will get my xi at k plus 1 step minus xi, and this bi will cancel out because bi and bi are same. So, if you see, I will get only summation. So, I maybe this minus this, so negative xi. So, from here I am getting minus aij x j k plus 1, if you see from here, minus x j. Okay. So, this one I can write divided by a I I. So, the same thing we are getting. So, minus plus, so I can take here the sign minus, just does not matter. So, this one I am getting. So, now from here you can check that this I can write as e k plus 1 I, the error at the k plus 1 step, and this is true for all I, 1, 2 up to n. So, this will be minus summation a I j, and everything is same, I from moving from 1 to n, sorry, j is moving from 1 to n, and j is not equal to I. Similarly, here j is moving from 1 to n, and j is not equal to I, and this will become e k j, this value, and divided by a I I. So, this is true for all I, this one. So, I got this relation. So, this is a error term we are getting at the, so I can write that this is the error term at k plus 1th iteration. Now, so you can see that I have E k 1, that is x 1 k minus x 1, E 2 k, that is x 2 k minus x 2, like this one. So, what I do is that I choose E k, that is maximum of all E 1 k, E 2 k up to E n k. So, I just take the maximum in this case. So, now from here I can write this equation as, so before that one I can just get rid of this negative sign. Okay, so I can just write from here. I can write E I k plus 1 magnitude. This one I can write as minus summation A I j E j k A I this one, and this can be written as, I know that this can be written as summation A I j E j k divided by A I. So, I have taken this modulus value inside the summation and I got this less than equal to relation. So, and this is true for all i's. So, that is understood. Now, from here, now I am going to apply this one. So, I can write this as E I k plus 1 modulus value is always less than. So, I am just taking summation. So, this one I can write as separate values A I j E j k divided by A I this value. So, now what we are going to do is that now I am going to take, so this is the value here. So, what I am going to do is this is, I will take the magnitude. So, I can write from here that summation A I j E k j divided by A I, and that is true for all j 1 to n and j is not equal to I. Now, I choose my capital E k as maximum of E 1 k. Actually, I have taken this magnitude E 2 k E n k, just have taken the magnitude. Here I am just showing this one. So, we have just taken the magnitude. So, now from here I can write this as, because it is coming in the each one. So, I just take the common. So, I can write from here that this will be equal to summation j from 1 to n and j is not equal to I, A I j and divided by A I taking this common A j k. So, this is E j k, I will just write here E k. So, this is the maximum value I have taken. Now, from here, now I will use the property of A. Now, since A is assumed to be diagonal dominant, which implies that AII modulus value that is going to be greater than summation A I j modulus value, and I will take j from 1 to n and j is not equal to I and I is moving from 1 to up to n. So, this one I am going to take. So, this is the definition of diagonal dominant matrix. So, from here I can write, so I just take this element here. So, I can write from here the summation j from 1 to n A I j modulus value divided by, and j is not equal to I, divided by A I modulus. So, it will be less than 1 for all I. So, this is less than 1. So, now if it is less than 1, so if you see from here, this term is same as this one. Now, from here I can write that E k plus 1 I will be less than. So, this terminology is here and this is less than 1. So, I can write that this is less than 1. So, from here I can write that this is equal to E k modulus value. Now, this is the maximum error at the kth step, and the error at the k plus 1 step in each of the xi is less than this one. So, which implies that the method is going to converge. Why it is going to converge? Because the error introduced at the kth iteration and the error introduced at the k plus 1 iteration. So, at the error at the k plus 1 iteration is becoming lesser than the maximum error at the kth iteration. It means that as the iteration will grow, the error is going toward 0, and so the error is going toward 0. It means that the matrix is going to converge. So, that is the way we have a sufficient condition that the given matrix is diagonal dominant, then the Gauss-Jacobi method is going to converge. Same way we can have the method Gauss-Seidel. So, this is one of the application of the diagonal dominant matrix. Another important application we are going to do is that all diagonally dominant matrices are non-singular. So, this is one of the another application. Suppose I take the matrix A, and this matrix is, suppose I take 5 by 5 matrix. So, like I take matrix 4 here, minus 1 0 1 1, and suppose I take 1 minus 6 2 0 1 minus 1 1 5 1 minus 1, then 2 minus 3 0 minus 9 2, and the last is 1 3 minus 2 minus 2, and suppose it is 10. So, this is a 5 cross 5 matrix, and if somebody asks me that whether this matrix show that whether this matrix is singular or non singular, then we have either we have to convert this matrix into the suppose row echelon form, and then from there I can say that if the rank of this matrix is equal to 5, then this matrix will be non singular. But it is just a 5 by 5 matrix, maybe it can be a 10 by 10 or 20 by 20. But now from here, if you check that this matrix is diagonal dominant, because this 4 is greater than summation 3, 6 is greater than 1 plus 2 4, 5 is greater than all the elements modulus value, summation of the modulus value, that is 4, and here it is 9 is greater than the 3 plus 2 5 plus 7, and this is greater than, because modulus value is going to give you 3 plus 1 4 and 4 8. So, this matrix is a diagonal dominant matrix, and from there I can say that this is a non singular matrix. So, that is the benefit of checking the diagonal dominance, because once we get that the matrix is diagonal dominance, then easily we can say that this is a non singular matrix. So, let us prove this one. So, how we are going to prove? So, suppose we have a matrix A that is diagonal dominant. So, suppose I take n by n matrix. So, this is diagonal dominant matrix. So, this is we have assumed. Now, we need to show that if the null space of A is just contain the 0 element, then we are done, because if we have seen that if the null space of a matrix contains a 0 element and the matrix is a square matrix, then the number of columns are linearly independent or the number of rows are linearly independent, and then it means that the rank of the matrix will be equal to the number of variable, that is n. So, now we are going to show these things. So, let we have Ax equal to 0 such that x is not equal to 0. So, I am taking the system Ax equal to 0, homogeneous system, such that assuming that x is not equal to 0. Now, suppose x is not equal to 0. So, let us assume that, so because x is there, so x is basically this one, x1, x2 up to xn. It is a n cross 1 system. So, let us assume that I just take here somewhere x k. So, let us assume that x k entry is of maximum magnitude. In x. So, let us assume that, because x is going to be a vector. So, suppose my x I take just as 1, minus 3, 4, 5. Suppose I take this one minus 4, or so in this case I will assume this value. So, let that is the my x k. Now, focus on the kth row of the system, because we are getting that the x k is the of maximum magnitude. So, I am talking about only the row corresponding to the kth. So, we are talking about the kth row only. So, let us take this one. So, now I am taking only the kth row. So, it will be equal to a k 1 x 1 plus a k 2 x 2 a k n x n, that will be equal to 0. So, I am writing the system A x equal to 0, and in that system I am taking only the kth row. So, this is my system, homogeneous system I am talking about, and from here I get this value. Now, I am going to write this system A k k x k and taking all the terms on the other side. So, that can be written as minus summation A k j x j, where j is moving from 1 to n and j is not equal to k. This is I am going to have. Now, from here I just take the magnitude, the modulus value. So, I just take modulus this value. So, basically this will removed, and this one I can write as a k j x j, and j is 1 to n, j is not equal to k. Now, this is coming with all values. So, from here I just take common, and I can write from here that my x, so I can write from here that the a k k x k is equal to a k j x j, and j is moving from 1 to n, j is not equal to k. This can be written as summation a k j, and this one I just take, because we have chosen that my x k is of magnitude larger than any of the component. It means I can write here x k, because x k magnitude is maximum of x 1, x 2, x n that we have taken. So, I have just taken this one and just taken outside, because otherwise it is coming with each member, but I have taken the x k in all and taken the common from there. So, I have just written like this one. Now, from here, now x k is not 0 of course, because it is a maximum value we have taken. So, from here I can write that my a k k is less than equal to summation a k j, j from 1 to n, and j is not equal to k, and this is true for all. So, here I am taking the k. So, this k can happen for any value. Now, k can be equal to 1, 2 up to n. It can happen everywhere, anywhere. Now, from here, if you see from here, then since matrix A is diagonal dominant, which implies, as we have shown in this case also, so which implies that the summation a I j divided by a I is less than 1. And j is not equal to I, and this is true for all. So, this is, I have just written this value, but here it is this one. So, from here I can just give the number here. So, maybe I can give it 1. So, from 1, which implies that the matrix A is not diagonal dominant. Because if it is diagonal dominant, then it has to satisfy this condition, because I can divide by this one, and this just it will be less than equal to 1, okay, because I can take this side, but here it should be only strictly that less than 1. So, from here I can say that based on this condition I can say that 1 is not diagonal dominant. Which is a contradiction. So, which implies that Ax is equal to 0 and so which is a contradiction means which implies that the x should be equal to 0 for Ax equal to 0, because we have started with Ax equal to 0 and we assume that x is not equal to 0, but from here we got the contradiction, means our assumption was wrong, we have to choose x should be equal to 0. So, which implies that the null space of A should contain only 0 element, and from here I can say that the matrix A is non-singular. So, the given matrix will be non-singular. So, that is the proof of this theorem. So, we will stop here today. So, in the today's lecture we have discussed the property that is diagonal dominant matrix, and based on that we have showed that how the iterative method, that is Gauss-Jacobi, has a convergence and how a diagonal dominant matrix is a non-singular matrix. So, we will continue with this one in the next lecture. So, thanks for watching, thanks very much.